Jerry Mahun is a licensed surveyor based out of Cuba City, Wisconsin, and was licensed in 1987. Jerry has spent years as a surveyor instructor, first at Penn State University in the Wilkes-Barre campus for almost 3 years, Madison Area Technical College as the program director for 19 years, and then couldn't retire, so he became a part-time instructor at University of Wisconsin-Platteville for almost another 6 years. So Jerry is a well-seasoned presenter when it comes to this kind of stuff. So I definitely appreciate your time again, like you have for the last few months, Jerry, and presenting another great topic for us. So I will turn it over to you, and thank you, sir.
Okay. Have I got the screen so I can?
You should be able to share. Yes, sir.
Okay, let me make sure that I'm sharing the right thing. Not the porn site. Turn that off. Okay. Okay, let's go here. All right. So share screen. And what I want to do is this one here. Come on, play. And then share screen, share.
There you go. It's coming up. There you go. Yep, that's your PowerPoint presentation. So
right. Okay.
Perfect.
So, all right. Based on what Trent was saying there is when we talk about the RTK, the GPS, and I've seen this happen. I've been in surveying long enough that I started back with transit and tapes. If anybody can remember that kind of stuff, reading verniers and stretching tape. And I was out surveying in weather as cold as 15 below with a steel tape. And that sucker shortens up quite a bit in that time frame, along with a couple of other things that shorten up. But I've seen a number of paradigm shifts both in my practice and in my teaching career, from transits and tapes to theodolites, and then digital instrumentation, the first EDMs that came along, and then the total stations, and now GPS and stuff. And it seems like with every paradigm shift, we're able to obviously make measurements more quickly and more efficiently. But there's also a higher dependence on the technology and a less understanding of the technology. Back in the days of a transit and a tape, you had that physical piece of equipment in front of you, and you could see all the parts of it. You could see where all the adjusting screws were on the transit, and you could see the effect of the tape, being cold and shrinking and expanding and things like that. But as we moved into electronics, we started losing that connection. And with GPS and LiDAR to a large extent, there's a lot of faith in the technology, and then on the manufacturer side and the vendor side of things. But the point is that regardless of the technology that we use, there are still errors involved with measurements. And a lot of the same ones that affected us back in the transit and the tape days are still affecting us today, whether you're using GPS, RTK GPS, or total station or whatever. So it's understanding, being grounded in the fundamentals and understanding why we do the things the way we do it helps us to understand how we can control those errors and make judgments based on them. And then also come up with a product that makes sense to our client. The surveying class I taught at UW Platteville here for the last couple of years was just a single class that all the civil engineers took. And I averaged about 90 students a semester. And most of them will never touch another piece of surveying equipment at all for the rest of their lives. And the idea was not to teach them to be surveyors. Heaven forbid you want an engineer out there with surveying equipment, but to teach them a little bit about where data comes from and something about the errors associated with it, because they may not collect the data, but they're going to use it to design stuff. And if they don't understand how weak the data is, or if they've got bad quality data, they can't make a good engineering decision based on that. And I'm sure we've all seen examples of that when you're out in the field trying to stake something and the utility pole's right in the middle of the road, or the water flows uphill instead of downhill when you put in a culvert and that type of thing. So the handout that I put together for today is about 18 pages, and it runs a gamut from the really basic stuff all the way through some basic concepts with least squares adjustment, because everybody's dealing with least squares now, whether you're doing conventional type of surveys or GPS or combining this stuff together. And there is an awful lot of territory to cover on this. So I'm going to kind of try to get through the first three categories tonight: numbers, measurement errors, and random errors, and then leave the least square stuff for next time. And maybe that'll help generate some questions that people might have when they start to see some of the basics that lead up into that for next week. So with that said, a couple of weeks ago, or a couple of months ago, I did a presentation on rules of construction, and we talked about conflicting title evidence and how we weigh the stuff. And I very neatly sidestepped, if anybody noticed or not, when things conflict, I didn't say how much they have to conflict in order for them to be a conflict, okay? So for instance, you get a description of a property line. It says to go 200 feet to a 1/2-inch iron pin. Okay. And out in the field, what you find is an iron pin, but with your total station, you fired off that distance and it's 175.24 feet. Does the pin fit the description? Is there a conflict between that distance and the distance in record, or is it the same thing? That's one of those things. What constitutes conflict? Now, the way we present numbers, and I tell my students this all the time, and we'll get into this a little bit more here in just a bit. We communicate with numbers. We leave, when we say we're following in the footsteps, the part of the footsteps that we're following in from the previous surveyor is the stuff that he or she wrote down in the form of numbers: bearings, distances, angles, quantities, and that type of thing. And we have to interpret from what was written what they intended. So I've got a distance here expressed as 200, and a measured distance of 175.24. So the question is that 175.24 feet within the uncertainty of that 200 feet? Because if it is, then that's the correct monument. If it isn't, then the monument conflicts with the distance. Now we have a dilemma. Which do we accept in that type of thing? Well, yeah, at the bottom there, I've got 200 written two different ways. I have it written as 200, 200, and 200.000. I'm 200.00 feet. And my question is, are those two distances the same? Anybody want to venture a guess on that? Come on, somebody guess. Silence. Okay.
Silence. I would say no, right? Because the 200 is to 200 is to an even foot, and the other one's at least to tenths or hundredths.
And that's another one of these things where when something's giving in round numbers like that, the question is that supposed to be an exact representation of that? And when we get into deed interpretation, there's all sorts of things like that we have to take into account. When we got conflicts between numbers, which are the numbers that control over the others, and that type of thing. But both of these numbers represent two things that they communicate to us. One is a magnitude, and the other is an accuracy. They both have the same magnitude. By magnitude, we mean size. They're 200 of something. However, how much of that 200, how accurate that 200 is depicted is different based on how those numbers are written down. To me, when I look at those numbers, when I see that 200.00 feet, those two zeros after a decimal point mean something to me. It means that to the nearest hundredth of a foot, the values are zero. It's not 200.01 or 199.99, it's 200.00. The 200, however, the way it's written, without any other indication, we're not sure if that's good to the nearest foot, the nearest 10 feet, or the nearest 100 feet. The way that's written right there by the rules of significant figures, which I'll cover here real briefly in just a minute, that's only good to the nearest 100 feet. So that's got an uncertainty of plus or minus 50 feet. If that's the case, then this distance here doesn't conflict with the record distance. It's within the uncertainty of the record distance. So again, when we put down numbers, we're conveying something about not just the size of that number, but the accuracy that that number represents. And that can introduce a dilemma for somebody later on. Now there's two kinds of numbers we deal with. Exact numbers and inexact numbers. That pretty much covers all of them, unless you're an electrical engineer, in which case exact and exact numbers weren't enough. You had to come up with imaginary numbers because plus or minus infinity is not big enough. An exact number is it's errorless. It has an infinite number of significant figures. There's no uncertainty in it whatsoever. And by using it with other numbers, we don't introduce any errors when we manipulate that exact number with the other. We do numbers like this, like counting numbers. If I were to say how many people are attending the session tonight, and I were to take a head count right now, I'd come up with an integer. I wouldn't come up with 19.3 or 21.6. It would be 19 or 21 or something. That's an exact number. We have some conversion factors that are exact. 1 foot is exactly equal to 12 inches. 1 meter is equal to exactly 39.37 inches for the survey foot definition. But 1 inch is equal to 2.54 centimeters exactly for the international foot. Those are two slightly different conversion factors. So anytime we use numbers like that or express those numbers, they don't introduce any error into what we're using them for. An inexact number has a finite number of significant digits. It basically is accurate to a certain level. Beyond that, whenever we use it, we can be introducing errors into our calculations if it's less certain than the numbers we're combining it with. And those are subject to errors. And a lot of them are approximations. We ask somebody, how big's the meter? And they say, a meter's about 3 feet. Well, it's not exactly 3 feet. It's 3.2808333 if you want to keep on going feet, if I'm more exact. But one meter is about 3 feet. It's an approximation. If I use that approximation to convert a certain number of feet to meters, my answer is going to be affected by the uncertainty or the approximation or the error in this particular conversion factor. Pi is equal to 3.14. 3.14157. I had a friend in grad school that had pi memorized to 500 decimal places. The guy had no life. All he could do was recite it to 500 decimal places, and he would do it at the drop of a hat. But the point is that if we use an approximation, it's subject to errors. Anytime we make measurements, measurements with our equipment, whether it's a steel tape or a total station or GPS receiver or whatever, those are inexact numbers. Those are subject to uncertainty. And the uncertainty is affected by a lot of different error sources, some of the stuff we're going to talk about tonight. And when we combine those with other numbers that are subject to errors, then we wind up with results that are subject to errors. And we talk about error propagation. All right, I just got curious. I always dumb laws and things like that come up. I came across this from 2017. This is today's, in history. And I said the bottom there, in 1897, the Indiana House of Representatives passed 67-0, a measure offering a new as well as fundamentally flawed method for determining the area of a circle, which would have effectively defined the value of pi as 3.2. Okay, so they decided this 3.1415 going on to infinity, that just didn't happen. So we're just going to make a 3.2 an exact number. So that not only shows that they didn't understand the fundamental concept of math, but they also didn't understand how to round, because if they're going to do that, they should have made it 3.1 instead of 3.2, or at least go all the way and make it just 3. But the point is, you can't take a number like that and turn it into an exact relationship without upsetting the apple cart with respect to a lot of other conversions and a lot of other relationships. All right, when we communicate in surveying, we communicate in a lot of written forms, but the two most fundamental forms that are there for posterity, that other people have to try to understand, interpret, and see what our intent was, are in the form of descriptions and in the form of maps. And sometimes the two are combined together. And we'll see all sorts of interesting things in descriptions. And I talked about this one back when I did the rules of construction. This is a description that gives GPS waypoints as the controlling terms for the property corners. And it gives the direction, it gives the latitude and longitude in decimal degrees to a certain number of decimal places now. And one of the things we discussed back when we talked about this in my presentation was, well, what kind of questions is that? How do you determine what the accuracy of that is? How accurate are those? What datum are they on? There's all sorts of questions that this raises. So even though it's a new technology, it's a modern technology, it introduces a whole nother layer of information. The bottom one is a part of a subdivision map. And I included this one because it does not have bearings shown to a tenth of a second or distances shown to a thousandth of a foot, like I've seen on some maps. But it does show, if you look down here, the area of a lot to a tenth of a square foot. Now, if you think about tenth of a square foot, that's not real big. Yeah. And you'll see that when you start to deal with errors, it's impossible to be able to determine something to a tenth of a square foot, although numerically, calculation-wise, it can. But then, again, you're conveying information, you're giving an accuracy that really isn't supported by the calculations and the measurements that went into it. But those are two major ways we convey information, numeric information, communicate it with respect to future generations. They have to try to interpret what we were talking about. All right, so I'm going to go through significant figures here very quickly. I'm not going to spend a lot of time on this. Most people are familiar with it. Most people have been exposed to it in some way, shape, or form. If you need additional information, I do have a whole section on it on my website. For those of you that aren't familiar with my open access website, there's a lot of information on it for surveying in general, educational material. But basically, significant figures or significant digits are all the numbers that we write down that we're certain of, plus one that's generally an estimate. And again, if we go back a couple of generations, a couple of paradigm shifts, a simple piece of equipment like the tape, it's a wonderful one to discuss errors and how we make measurements and that type of thing. And if I've got this tape that's stretched out between two stakes in the ground here, and at one end, this is, it's divided into tenths of a foot. We're not divided into hundredths of a foot for this one. So I can read directly to the nearest tenth of a foot what that distance is. So I know it's 99.8 something feet, between 0.8 and 0.9 feet. So I can say directly, I'm certain of the 99.8 feet. I can interpolate between these two and say, well, that looks like it's about 4/10 of the way over. So I'm going to guesstimate 998.4. So that last one's an estimate on my part. So that number, as I presented, has got four significant figures. The three that I'm certain of, and the fourth one that's an estimate. Now, somebody else might look at that and say, well, it looks more like a 3 to me, or it looks like it's pretty close to a 5 to me. If somebody says that's a 0.45, you're really pushing it at that point. But that last one's an estimate. Okay? Now, if I were to divide this tape down into 100ths of a foot for the division, I could give it to the nearest hundredth of a foot with certainty, and then I could estimate the 1,000th of a foot. So every time I've got a division that's on there, if I make another division, a tenth of that, I can always go an additional step on interpolation. At some point, you just can't see it anymore. That's sort of like on the old transit, you had to resort to using a magnifying glass to read the verniers because the divisions were so small. I said, well, wait a second. I don't use a steel tape. I use a total station. Okay. And my total station's got digital readout. So I don't have to worry about significant figures and all this kind of crap with estimates and all that type of thing. It reads it out to me to the nearest second. Well, this is one of the instrument types that we were using here at Platteville. It's a Sakia Set 62, a relatively recent piece of equipment. And it can be set up to display angles to the nearest second and distances to the nearest thousandth of a foot. Now, if you look at the specifications for it, the display resolution can be set to 1 or 5 seconds, but the accuracy, according to the ISO, is 2 seconds. So really, when I say I'm going to show it to the nearest second on there, does that second really a reflection of the accuracy of that equipment? And as a matter of fact, in the context of this ISO description of the angle specification, that's not really the same as back in the days of theodolites and transits. We had a physical marking that was on a circle, either a metal circle or a glass circle. And when we said we had a 2-second instrument, that meant the smallest division on that circle was 2 seconds. Well, a total station does not have metal circles in it. It's got encoders in there. And it's actually using an electronic way to read both sides of that. So the resolution is different than the traditional resolution we're thinking about. But basically, this is what the specification is that the manufacturer stated expected error in one aspect of measuring the angle is. So even though I can show it to 1 second on here, that doesn't necessarily mean that angle is good to 1 second, nor is that distance good to nearest hundredth of a foot. Okay? So just because it's a digital display doesn't mean that every single digit that's on there is in fact significant or a reflection of the accuracy of that instrument or the angle or the distance that was measured. So we still got to take things a little bit with a grain of salt. Now, which digits are significant? And I'm just going to run this real quick. Any non-zero digits are significant in a number. Whenever we write it down, 1, 2, 5, that's got 3 significant figures. The problem that people have are with zeros, when they're significant and when they're not significant. They're significant if they're between non-zero digits, or they're to the right of a non-zero digit and to the right of a decimal point. This is like that 200.00 that I had. These zeros out here mean something when I put them out there. That says to that level of resolution, the nearest digit to it is 0, not 9 or 1. If it's to the left of a decimal point and to the right of a non-digit, we don't see that to a non-zero digit. We don't see that one too much more. Where they're not significant is when they serve only as placeholders. Placeholders help determine magnitude of a number, but they don't help determine the accuracy of that number. I can take any number, 1, 2, 4, and stick as many zeros in front of it as I want. That doesn't change the accuracy level of that number. It's only good to the nearest one. So that's only got 3 significant digits. This 0.000098, all these zeros here serve to do is to tell me what the magnitude of the significant digits are way out over in here. Where it's really confusing is, again, when you have numbers like on that 200, 200, without any indication of decimal points or anything like that, is which is significant. In this case here, only the 4 is significant. The zeros are really placeholders. But what if this 0 is significant and these other 2 aren't, or this one is and this last one isn't? Then we have to come up with alternative ways of displaying it. But the point is, when we're dealing with zeros, if they serve only to set the magnitude of the number, they're not significant. They're only significant when they help identify the accuracy of the number. Now that we all significant figures, how do we combine numbers together? How does that affect what we get coming out of the end? Well, adding and subtracting, and I love the quote, the textbook I used to use, the textbook for the class. They always, when you read about adding and subtracting, it says that the significant digit, the furthest to the left in the addend, will be in the same column as the last significant digit, the furthest to the right, and any of the numbers being added together. Which in English means it can't be any more accurate than the least accurate number. Okay. Now I'm sitting here, and from me to Dubuque in a straight line here is about 26 miles. Okay. All right. I have a tape measure here. Okay. I'm going to move exactly 1 foot back from where I was sitting. Okay. How far is it from here to Dubuque? Anybody want to give me a guess? No guesses.
About 26 miles.
About 26 miles. The fact that I moved exactly 1 foot further away or 1 foot closer doesn't make any difference, because that's more accurate than the least accurate number I'm dealing with, which is the 26 miles, right? So when you look at adding numbers together, the answer can only be as accurate as the least accurate number you're dealing with. So when I add up these numbers that I show in the column here, then my calculator is going to tell me it's 1,141.54 feet or units or whatever it is. It's up to me to decide which of those numbers are garbage numbers or not. So in this case here, because my 100 is the least accurate over in here, that means this number can only be good to the nearest 100. So this, when I add it all together, is only good to two significant figures, 1,100. So then, and that, whether I'm adding or subtracting, whether I move exactly 1 mile closer or exactly 1 foot closer or 1 foot farther, it doesn't affect the fact I'm still 26 miles away from Dubuque. When you multiply or divide, it's a modification of the addition rule. The product will have the same number of significant figures as the least number of significant figures in either of the numbers that we're multiplying or dividing. So in this case here, when I got 13.1 times 147.25, I get my calculator give me this raw answer of 1928.975, but it's up to me to decide that, well, the 13.1's only got 3 significant figures. So that means my answer can only have 3. So my answer's got to be 1,930. And this is one of the places where people get tripped up. Is it, if you're using a conversion factor that's exact, let's say, for instance, I got this 1,147.25, say that's in feet. And I want to convert that to inches, which would mean I would multiply that number times 12. So I'm multiplying 147.25, which has got 5 significant figures, against 12, which has got how many significant figures? Infinite, it's exact. So only, and my answer is going to have 5 significant figures because the number that I'm converting with is my exact conversion factor. So you always got to be looking at which is the one that's got the least number of significant figures. That's the one that's going to affect the answer I come up with. And then chain calculations are just merely a modification or a combination of these particular rules here. Where we run into problems with significant figures is not just in recognizing how many the answer can have, but when we're doing chain calculations, wind up doing intermediate rounding and having that bias our answer when we get to the end. We see this happen all the time when people are doing long calculations, and they still like to write things down in stepwise fashion and do intermediate calculations and then go from there because they can keep it straight. And that's fine. Well, let's say in this case here, we have an area that we want to compute the square yards of it, a rectangular field that's in feet. And we had 65.32 feet times 130.19 feet. And well, 65.32's got 4 significant figures, and the 130.19's got 5 significant figures. Now, one way to approach this is to convert each dimension to yards, then multiply the yards times yards to get square yards. Well, that's what a lot of people like to do, kind of see the steps way through there. So if we take the 65.32, and I remember the 1 yard, 3 feet, that's an exact conversion factor, so that doesn't affect the accuracy. We get 21.7337, and I'm going to take this out to 3 figures here. And I'm going to do the same thing with the width, 130.19 times that, come up with this. I multiply those two together and I get this. And because I've got 4 significant figures here, I'm going to round my answer to 4 significant figures. So I get 946.1 square yards, piece of cake. Another way I can do this is the same thing, except I don't do an intermediate calculation. I just go straight through. I take the length, the width, times a conversion factor, times the length, times its conversion factor. I come up with this number and I round to 4 significant digits. I get a different number. I get a substantially different number. I get a number that's different by 1.2 yards. Okay? When you're doing earthwork calculations on a long project and that type of stuff, those couple of cubic yards adds up after a while. And pretty soon you're talking thousands of cubic yards of material that either doesn't or doesn't exist. The reason this happened is because there's this intermediate rounding, which is biasing our numbers as we come through. It comes out looking correct. The magnitude is about right, but the accuracy is off because of this internal rounding and that type of thing. That's generally where we see most of the problems with doing manual calculations. And even though you're keeping track of significant figures, that internal rounding in a long series of chain calculations will have an effect. So what we normally tell students to do, or anybody else that does calculations, is to either carry at least an additional significant figure in your intermediate calculations, or better yet, use the memories on your calculator and don't write any of those numbers down, just run them all the way through and then round when you finally get to the end. It makes a big difference in a lot of cases. Using the wrong conversion factor is also another one. And I've seen this on some of the review material I've seen for the licensing exams and for the CST exams and that type of thing, where they're asking the metric conversion for something, and they're using the international foot conversion as opposed to survey foot. Now, for small distances, that doesn't make much of a difference if I'm converting the length of a tabletop. But if you're working with state plane coordinates, which are in the millions and the hundreds of thousands of feet, and you use the wrong conversion factor, it can throw you off considerably, because the difference between the two is about 1 in 500,000. So you'll see it in big numbers like that. So using a wrong conversion factor, and if you use a conversion factor it's built into your calculator, it's going to be the international foot one. It's not going to be the survey foot one. We actually in Wisconsin are required by law for all of our surveying legal documents and stuff to use a survey foot definition. I don't know if that's true in all states or not, but we actually have it written into our subdivision regulations and stuff that affect all of our surveys. So, and that's all going to go away eventually anyway, but that's a whole other story. All right. So now when we talk about the quality of measurements, there's a couple of words that we toss around all the time and kind of interchange them. And when I hear this on TV, I always get real upset. My wife tells me I have to stop yelling at the TV because they're not using the word precision accurately when they're talking on TV. But basically, we have accuracy, precision, and another related one I'm going to call it resolution. Accuracy is the absolute nearness to the true value. And the more accurate a number is, the less error it has in it. Okay. Now, this deals with measurements and non-exact numbers. Exact numbers are error-free, so they're accurate to begin with. Precision is not accuracy, it's repeatability. It's when I repeat a set of measurements, how often or how well do I come near that same thing all the time? Am I consistent? What am I doing, or am I all over the place? It's a behavior, and that behavior is reflected in a lot of things. Resolution is kind of related to both, and is sometimes used in lieu of accuracy or in conjunction with accuracy. We think of resolution as the smallest division to which a measurement can be expressed based on the equipment that we're using to measure with. Now, again, I use my tape here, and if I measured that and I've got a tape that's divided to 1/10 of a foot, I can, using significant digits, give an answer consistently to the nearest 100th of a foot with interpolation. So my precision there, 9.84, 9.83, 9.84 is pretty good. I'm pretty close every time I measure that. Okay. Now my accuracy in terms of resolution is I'm expressing that to the nearest 100th of a foot. That's my resolution. If I've got a tape that's divided to 100th of a foot, then I can express my resolution to the nearest 1,000th of a foot. So I'm getting closer and closer to what the true value is because my divisions are getting smaller, but that doesn't necessarily mean I'm eliminating my errors. Okay, I could still have errors, or I might have smaller errors with the smaller divisions, meaning my number is more accurate, but it doesn't mean that my errors are all gone away. So sometimes we'll use terminology like, well, it's accurate to the nearest 100th of a foot. So we kind of couch it in those terms and that type of thing. So resolution really isn't actually, it's the type of equipment that we're using to measure the particular thing that we're trying to find out. All right, so we use the traditional targets to express to show the interaction of accuracy and precision, primarily because it's a good visual indicator, and the other reason is because people like to shoot at stuff all the time. So when you can relate it to something that they're familiar with, they can immediately see what this difference between accuracy and precision is. Okay, I've got 4 targets up here, and I've got a person that was shooting at each target, and they each took 4 shots at the target. So part A, on target A, you see a pretty tight shot grouping, and it's pretty close to the bullseye. Now, they were aiming to hit the bull, right? So what can we say about the precision of that person's shot group? Good, bad, indifferent? Not nodding doesn't work, folks. I can't see.
it's pretty good because they're all grouped together. So
Yeah,
that
it's
would
pretty good.
indicate it's precise.
Yeah. How about accuracy?
Yeah, it's accurate too because they're all on the center where they intend for them.
Now, the reason they don't go through the same hole dead center in that bowl is because there's some errors that are still in there, right? There's still something wrong. How about B, that person right there? What can we say about that person's precision?
Precision is fine.
Yeah, the precision's fine, right? What about the accuracy?
Yeah.
No, it's not good. They were aiming at the ball, but they were consistently hitting away from it. So that tells us that there's something that's being consistently off with respect to that shot, that person that's shooting there, right? It's either in the equipment or in the person, and we'll get to some of those things later on. How about C? What can we say about the precision there?
Precision is not good.
Precision is not good. What about the accuracy?
Not good.
Oh, take the average of those 4 shots. Where does it put them?
Oh.
See that?
Yeah.
That's what we call accuracy by accident. Okay. Eventually, that person's going to hit the bullseye, but not by design, but by accident, right? So the precision is all over the place. It's not very precise, but it is in fact accurate. What about D? Precision is what?
Bad.
Bad. Accuracy is what?
Not good.
Not good. That's a shop vac accuracy. It sucks, right?
Yeah.
So we have a demonstration here of the 4 combinations of stuff that we can have: precise but not accurate, accurate and precise, not precise but accurate, and not precise and not accurate. Those are really the only 4 that can happen when we've got a set of measurements. Okay? Now, let's see. Okay. All right. Now, when we talk about resolution, again, I talked about this briefly before. The higher resolution, in theory, gives better accuracy because we're having a smaller and smaller range within which we're expressing that measurement. So, again, if I've got a protractor that's divided to the nearest 10 degrees, I can interpolate to 1 degree. So that makes my error small in that respect. If I direct to 5 degrees, I can interpolate to 1 degree, maybe even smaller than that with a 5 degree division here, maybe the nearest half degree. And here, if I've got 1 degree, I can interpolate, that really should say 0.1 degree, not 0.5 degree, but I can maybe interpolate down to 1/10 of a degree. But at some point then, I'm also trusting that the divisions themselves are spaced uniformly and that there's no error in the equipment itself with which I'm making the measurements, which is what we'll get into when we talk about error sources here in a bit. Okay. All right, so the basic error tenants, and every textbook has this in there, and I have to kind of qualify this a little bit. I'm going to say this is for individual in measurement. Whenever I measure something, make a measurement of like the length of a tabletop or the elevation of a pointer, that type of thing. No measurement is exact. We know that. Every measurement contains errors, and the true value of a measurement is never known. If it was known, we wouldn't be measuring it in the first place. I mean, you kind of think about that. So the exact error present in a measurement is unknown. Now, my qualification on that is, if I'm measuring the angles of a 3-sided parcel, okay, and I'm going to add up all, I know that each of those individual angles is going to have error in them. But I know that those angles have to add up to what?
$360 degrees.
Not a triangle, not triangle, 3 sides. I want to make it simple.
There you go.
Okay.
180.
Yeah, 180.
180.
Sorry.
It has to equal exactly 180 degrees, right? For plane trigonometry. So I know I can say, if I add up all those angles, they come up to 179 degrees, 59 minutes, 20 seconds. I know that there's 40 seconds of error in my angles, right? I just don't know which angles they're in. But I do know that the amount of error that's present, I just don't know in the individual measurements what the errors are. So when I'm talking about these error tenets, that's why I'm saying individual measurements. When I run a level circuit and I close back on my benchmark and I close off my benchmark 0.05 of a foot, That's the total amount of error in that level circuit. But I don't know what the amount of error is in each individual elevation that I determine throughout there. But they all contribute to that closing elevation error that I have. All right. Now, error sources are where they come from. First of all, there's the environment. That's the natural, that's within which the measurements are made. You know that when you're out there and it's 70 degrees outside and sunny and a little bit of a breeze blowing, you have a certain amount of comfort working out there, as opposed to if it's right above freezing, it's sleeting out there, and the wind is blowing, and you know everything's sticking there. You know that that's going to affect the quality of your measurements, simply because it's more of an adverse situation to work in. And I have had bears sneak up behind me before and something. You guys probably had things like that happen too, but you do wind up with situations it's really uncomfortable to work outside, and when it's uncomfortable, you can't get real good measurements completed. Instrumental is the equipment that we're actually using to measure with, and that's generally an indication of not that we're using the right or the wrong kind of equipment, but we're using equipment and using it in a fashion where it's maladjusted and we're not compensating for that maladjustment. When I first learned surveying many years ago, we learned to measure distances with a steel tape. And there are two kinds of steel tape for those of you who go all the way back. There's a cut tape and there's an add tape, right? Cut tape, you subtract the reading to get the last partial tape length. The add tape, you add it to there. Well, we had a particularly sly instructor who would always repair tapes when they broke and that type of thing. And what he did was he patched together one end of an add tape to another end of a cut tape. So depending on which direction you were taping with the tape, you either had to cut or you had to add. That was just a piece of equipment. But you know, if somebody had a tape that had a foot missing out of the middle of it and it was mended together, then every distance that you measure with that that's over 45 feet long is going to have a 1 foot error in it. Every distance that you measure that's less than 45 feet or less than 43 feet will not have that 1 foot error in it. Okay? If you ever look, this isn't as common anymore, but it used to be with the older instruments with the exposed adjusting screws and that type of thing. It wasn't uncommon to sometimes look through a scope and see your crosshairs up, tilted to one side and kind of rotated and that type of thing. That's an instrumental error. Now you can still use that equipment if you know how to do it, but that indicates that there's a maladjustment in the equipment. Collimation error is something that's relatively common with levels. Is the presumption is that your line of sight coincides with the horizontal line where the instrument is leveled. Well, that's not necessarily the case. If you have a collimation error, your line of sight could be inclined or depressed, and you're going to introduce an error into every backside or foresight readings you're taking with it. And a presumption that your bubbles are an adjustment on, say, a total station or the rod bubble that you're using with your GPS receiver or your reflector and that type of thing. When you center it, it's out of adjustment and your instrument's no longer oriented with respect to gravity correctly. So that'll introduce an error. An error comes from those sources. This is where they're coming from. This is not necessarily how they behave and how we compensate for them. And the last one is personal. The people that are using the equipment. Are they using it correctly? Do they know what they're doing? Have they got the bubbles centered correctly on the automatic level? Did they, and this happened a lot with my students and stuff, they wouldn't extend the level rod all the way out, and you'd wind up with a disjuncture between the lower part of the rod and the upper part of the rod. It looks like it's consistent through, but you see it's missing a whole bunch of feet in here because the rod's not extended all the way out. That's just a person making a mistake. So if you look at the sources of errors, it's the people who are using the equipment under specific environmental conditions. That pretty much covers the whole 9 yards with respect to where errors come from. Now, how they behave, however, is different. They may come from different places, but how they behave tells us how we're going to deal with controlling them. Or if we can't control them, how we can eliminate them. And if we can't eliminate them, how we can analyze them to see what their effect is on our measurements. The three types of errors are a mistake, a systematic error, and a random error. And not everybody considers a mistake an error, but in the classic sense. But I consider it an error because anything that detracts or disallows you from coming up with the correct measurement for something, it to me is an error source, a type of error. And the mistake is just that. And the mistake is carelessness or misunderstanding. When they didn't extend the rod all the way, that was a mistake, and that introduced an error. A systematic error is one that conforms to a mathematical or physical law, which means that if we know the conditions under which that error occurred, and we know the conditions under which that error doesn't exist, and we can compare the two, we can figure out how to compensate for that error. And we'll see different ways that we can look at that. And then once we eliminate all the mistakes and compensate for all the systematic errors, the only error that are left, the only errors are random errors. And they tend to be small. And they tend to be as likely positive as negative. Like if you think back to when I was showing that interpolating those readings on that steel tape, that last digit varied a little bit each time I measured. Well, that's the random error, and they're bouncing around what the true value is. And if I measure it enough times, I'll get a pretty good representation. A really good example of how random errors behave is flipping a coin. If I flip a coin once, it's going to come up heads or it's going to come up tails. If I flip it twice, it's going to come up either heads, 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 tails, tails, heads, or tails, tails. When I flip it again, there's more combinations, but in each combination, I'm going to find out that there's about half the time it's going to be heads and half the times it's going to be tails. And the more times I do that, the greater I'm going to get to that 50-50 cutoff between the two. So that's got perfect offset. And I tell my students, if you flip a coin an infinite number of times, it's going to come up half the time heads, half the time tails. I can guarantee it. Now, those don't believe me, tell them to spend their time in their dorm room this weekend and flip a coin a million times, infinite number of times, and count and see what happens. But that's how random errors behave. You give them a chance to compensate through sheer numbers of repeated measurements and that type of thing. So now, if we look back at our targets here, we're looking at precision and accuracy. Now we know a little bit about some of the things or where the errors could have come from and how they would have behaved that would have affected how these shot groupings work. So in this case right here, on that very first one, where we had good accuracy and good precision, the systematic errors have been compensated. There are no mistakes in there. And the only thing that's preventing us from going dead center on that bullseye with all four bulls in the same hole are the presence of random errors, okay? The better we get at it, the more we do it, the tighter and tighter that shot group's going to get together because we're minimizing the random errors. If we look at this one at B, what does that indicate to you that's happening? Those of you that are hunters, if you had a shot group like that,
your scope is off.
Yeah, your scope is off or your sights are off. So how would you compensate for it?
You would adjust your sights or your scope.
Yeah, you either adjust your sights, mechanical, you fix it. It's an instrumental error, or you adjust the way you're aiming. So instead of aiming at the bullseye, you would aim up and to the right, correct? To bring that shot group. So you're either doing it mechanically by adjusting the equipment, that's an instrumental error, or you're doing it by procedure, okay? By compensating for that instrumental error by how you're using that instrument. So you got the accuracy down. I mean, you got the precision down pretty good. The only thing that's preventing you from getting good accuracy is the presence of at least one systematic error in there. This one down here, the accuracy by accident, that's primarily incorrect procedures. When students first learn how to work with equipment, they're doing this all the time. because they're not used to the processes that we use to try to minimize the errors, which buttons to push, which slow motions to lock and release and all that kind of stuff. So they're all over the place. So that's one that comes with experience. With the more you work at something, the better you become at it. And this one right here, it was just a mistake to let the shooter near a weapon. That person had no business at all doing what they were doing. They're either not under the right conditions or with the right type of weapon or the right type of procedures and all this kind of stuff. There's a lot of work that has to go with this person before they can be trusted to start making, doing those shots and that type of thing with respect to that ball. You don't just start randomly shooting at things. At least you're not supposed to. All right, minimizing. To minimize it with a mistake, we generally, with a single measurement, you can't tell if a mistake was made. If you measure something once, you're assuming that no mistakes were made and that the numbers I've got are a good indication of what that thing actually is. So here I got a steel tape, 170 degrees Fahrenheit outside, 20 pounds pulled consistently throughout, and I measure a distance, I get 362.24 feet. Ta-da! How can I be sure no mistake was made? Well, I'll measure it again. So I measure it again. And this time I come out and I change conditions entirely. I come out when it's colder. I've still got a steel tape, so using 25 pounds of pull, but now I get 262.19 feet going in the other direction. What happened? Did the temperature make that much of a difference? How many of you have ever measured with a steel tape? Okay, if you have, you'll know exactly what happened here. How much of those different distances differ by?
Exactly 100 foot.
Almost exactly 100 feet.
Somebody forgot to count one of those.
Yeah, you either counted one, you add an extra one in there, right? So one of them's 100 feet off. Okay. So the question is which is the right one? Well, I'll just take the average of the two. No, you don't want to take the average of the two, because then what you're doing is you're taking the mistake that's in at least one of them and you're spreading it into both of them, right? So you want to get rid of the mistake. Well, the only way to get rid of the mistake is to do what?
Do it.
Measure it a third time, which is why we always measure things at least 3 times. So we measure a third time. Hopefully, that third time that we measure it is going to come close to one of the other two and not be a third different number entirely. Because if that's the case, then it's time to hang up our shoes and go find maybe a different career path and that type of thing. So we measured a third time in order to figure out which one is the mistake. And we'll toss the one that's got a mistake. So generally with mistakes, to get rid of mistakes, we remeasure until they're all within some sort of accepted tolerance. And that tolerance can be defined based on the type of equipment that we're using or the type of accuracy that we need for a job or that type of thing. We might say that when I had my students do a pacing lab, one of the very first measurements that they did, I told them they had to pace their distances on the baseline and on the unknown distances until they could achieve a precision of 1 in 50. So they had to keep pacing until their range of numbers were within that. Anything that was outside that 1 in 50, you would throw, because you don't want those numbers to pollute the mistakes, and those to pollute the numbers that you are keeping and that type of thing. So you repeat it enough times until you're comfortable with that it's within whatever your accepted tolerance is for that particular type of measurement. For systematic, you apply either a mathematical correction, a mechanical correction, or a procedural correction. And we saw that with that bullseye, with the target one, there was 2 ways we could do it. We could do either mechanically by adjusting the sights, or procedurally by changing where we aimed. Now, we really can't do a mathematical correction there. Well, I suppose we could. We can say, yeah, I was good. I was four inches below and 3 inches to the left. So mathematically, I was pretty darn good, in that respect. Normally, that doesn't cut too much with respect to that. But there are situations in surveying that we can do a mathematical correction to compensate for a systematic error. Now, when we do surveying procedures, it's a specific procedure that we follow when we're doing types of measurement to ensure two things. One is that the measurement is made correctly, so we're collecting information we need to collect, and that if there is a systematic error that can be compensated procedurally, we're doing it in a fashion that allows that error to be compensated. And an example of that is level collimation, line of sight collimation for a level. If our line of sight is inclined, let's say like this example right here, that means our crosshairs in our instrument are set too low, which is inclining our line of sight. So we're not sighting horizontal, we're looking above, but it's along a straight line. So it's a function of distance. The further away from the instrument, the greater that error is. Now, we don't know if that's in there unless we perform a peg test or something along those lines that allows us to compare known elevations against each other with respect to our instrument. So we can adjust that. When we do a peg test, we can actually at that point then adjust our crosshairs to make it read the correct reading on the rod when we're completing a peg test. So we can physically adjust it by using the upper and or lower adjusting pins or adjusting screws on the reticule. Most modern instruments, this is a spring loaded at one end, and you just need to turn one to raise or lower the crosshairs. But in a lot of cases, that's a little bit of dick around, not too much of a collimation error. The other thing that we can do is we can do it mathematically. Is part of the thing that we can figure out is if we know from the peg test what the error is and what the distance is, we can figure out a collimation error rate. And then we'll call that C. And then if we multiply that C times the distance to the rod, that'll tell us how much error there is in the rod reading. So we can then add that to the rod reading to correct it. So in this case here, it would be a negative correction that would be added, or be a negative correction that would be added to our reading at this distance to get this correct reading here. The drawback to this is that you have to have the distances to the rod. And pasting's probably good enough for that, or if you're doing 3-wire leveling, you're automatically capturing those distances, but you got to have that distance, and you also have to have a peg test in the first place. Well, we can also deal with it procedurally, and this is why we always balance back sights and foresight distances in differential leveling, is because whether our instrument is an adjustment or not doesn't matter. If it's not an adjustment, then if the back sight and the foresight distances are balanced, then the back sight error will be the same as the foresight error. So in this case, we're adding that error, and then we're subtracting that error. It goes away. It's compensated for. And we don't even have to know what the error is or if there is any error in instrument. So we don't need a peg test on this to do it. So this is a case where we can do it one of three ways: adjustment, the peg test, just a crosshairs. We can we can compute the collimation error rate and apply that out in the field mathematically, or we can just deal with it systematically. The only problem with dealing with it systematically is the error isn't canceled until we subtract it off of here. The height of the instrument here, the elevation of the instrument here, is still an error by this amount, which is why we don't do a whole bunch of shots off of this one guy here, because we always want to do a balanced backside and foresight to make that error compensate. If we're doing short sights off there, short side shots off of there, then it's not compensated, which is why back in the old days of profile leveling, whenever we did take side shots off of that to the center line and the cross sections, then we only run to 1/10 of a foot because of the ground it was sitting on and the fact that they were unbalanced sights. Right? Now, there are other examples in surveying that we use procedures for specifically to allow systematic errors to compensate wherever they occur. Earth curvature and refraction in leveling are the same type of thing like collimation. They're a function of distance. The further away they are, the greater their effect is. Now, Earth curvature and refraction isn't linear, neither is curvature. So it's not just simple linear relationship, but if we balance our backsight and foresight distances, their effect goes away. Now we can compute what they are, we can apply them. If we have no the distances to rod and that type of thing, we can't adjust it out because that's a natural thing, that's not an instrumental thing. Also with total stations, double centering, studying a line by double centering, or plate bubble run. When you're leveling an instrument and the plate bubble runs 2 divisions, when you rotate the instrument 180 degrees, you bring it back half that amount, 2 divisions, you're compensating procedurally for an instrument whose bubble is out of adjustment. Double centering deals with the fact that the horizontal axis and the line of sight are perpendicular to each other. And you're compensating for that by reading on both sides of the instrument. So in one case, it's on one side, in the other case, it's on the other side. And your average between the two compensates for that error. So that's why we do things in a particular fashion in surveying, is to allow those systematic errors to compensate the process. Once we eliminate the systematic errors and the mistakes, the only thing that prevents us from coming up with exactly the same number each time we measure and a true value is the presence of random errors. And the way we minimize random errors is by using the appropriate equipment for the accuracy that we're shooting for, that we have knowledgeable people using that equipment, that we're using it under favorable conditions, and then we repeat the measurements sufficiently to allow the major effect of those random errors to compensate, because there's likely to be positive as negative. We're like the flipping the coin. The more times we flip it, the closer we get to that 50-50 breakoff between the two. So this is an example. This goes back to the old Federal Geodetic Control Subcommittee triangulation angle measurement specifications, the old FGCTS specifications back in '84. And I pulled this out. This is for measuring angles. This is some of the specifications that they had in there. And based on the order in class, first order being the highest and third order class 2 being the lowest of the formal orders. And each position is a direct and a reverse reading. So for, say, first order, you had to read 16 direct and 16 direct and 16 reverse angles, 32 total angles. The maximum standard deviation of the mean, and we'll talk about that later on. But now we're getting into what are the rejection criteria. The farthest they can be away from the average is 4 seconds, okay, from the average set of our readings and that type of thing. So when we get into third order class 2, the number of positions is only 2 direct and reverse. That's only 4 angles. The standard deviation maximum is considerably higher, and the rejection limit is now 5 seconds from the average. Now some of these have got double like this one here, depending on the type of instrument that you're using. One of the other differences is for those of you that old timers and that type of thing, when you did these positions and for first order and second order class 1, you had to do them at night. You couldn't do them during the daytime because of the heat waves and that type of stuff. So you had to do it at night, and you had to cite lit targets and that type of thing. So it was real interesting times back then. But that's some specifications that help us determine when we have sufficient measurements to help those random errors compensate. This is just a quick and dirty plot I put together based on the DIN specifications for particular instruments and repeating the angles a number direct and reverse set. So in this case here, the black line is a 2-second DIN instrument. Next one's a 4, and the other one's a 6. So theoretically, this one is 3 times, it's got the 3 times the resolution of this one does here. And you can see that repeating the angle, the first couple, these are a direct and reverse set, so each represents 2 measurements. When I'm down here at 1 direct and reverse, you can see that there's quite a bit of error that are in these angles. You know, 8.5 seconds here, 5.5 here, and almost 3 seconds here. But as soon as I start repeating those measurements, notice how they drop down very quickly, and they get closer and closer together. Now, you reach a point where there's diminishing returns. There's a much greater increase in the accuracy here for the first couple repetitions than there is down here for these right in here. So that's why you'll see that not only they get closer and closer together, but after a certain point, it's just not worth it to do that. You don't have to be out there an infinite amount of time to make measurements before you start to get good repetition to allow those random errors to compensate. And this is for a total station angle measurement. This is true for anything where there's any random errors. You'll see that initial drop off quite a bit, and then they'll start to level out. You reach that point of diminishing returns. So to minimize errors, favorable conditions, use proper equipment, train personnel, correct procedures, and repeat measurements. Okay. And this not only, this won't eliminate errors, but it'll minimize them. And the ones that are left should be random errors, and they should be relatively small. Okay. All right. With that, let's move on to, so let's go do some basic analysis here with this. So now we're going to assume that we've compensated, we've gotten rid of all the mistakes. We've compensated for all the random error or the systematic errors. The only thing that's left are the random errors. And what we want to know is how do we look at that, and what does that spread of numbers tell us with respect to our expected accuracy and the precision of what we're dealing with, and how can we use that in conjunction with other things later on. Now, there's two types of measurements that we make in surveying, and they don't make much of a difference at this point right here. They will later on when we talk about least squares and least squares adjustments, but there are direct measurements and there are indirect measurements. And the easiest way to think of them is a direct measurement is I'm measuring the thing that I want to know. Okay, so it's like the distance between two stakes. I pull out my steel tape or whatever, my total station, and I measure that distance directly. There's no calculations involved. It's measuring that thing. The only calculation that might be involved is if I'm applying a correction for a systematic error. Like say in the case of a steel tape, it might be that I'm applying a temperature correction. If I'm dealing with a total station, I have to put in my temperature and my pressure to put in the atmospheric corrections and that type of thing, but I'm still measuring it directly. An indirect measurement is something that I need computations to get from the measurements to the thing that I want to find out. So there's that intermediate step. So the simplest one is differential leveling. I want the elevation of B. I don't measure the elevation of B directly. What I measure is the height of my instrument above point A and the height of my instrument above point B. And then through math, I transfer the elevation from A to B through the series of math and measurements and that type of thing. So that's an indirect measurement. Like I say, right at this point, that's not going to make that much difference in this basic analysis. But it does make a difference when we start to talk about least squares and network adjustments and that type of thing. Okay. Now, a redundancy. A redundancy, also known as a degree of freedom, is a measurement beyond what we need to know to determine a quantity. Okay. Example, the horizontal distance, if I want to know the horizontal distance between 2 points, all I can do is measure it once, and I've got the measurement that tells me the distance. Now, I have one measurement and I have one unknown, the unknown being the distance. I have zero redundancy. It's the number of measurements minus the number of unknowns. If I want to track down mistakes, then I'll run that measurement again, maybe in a different direction, under different conditions, or a different piece of equipment. I'll measure it a second time. That gives me two measurements for the same unknown. So now I have one redundancy. So every time I measure something again, I add another redundancy to it. Okay. How many redundancies do I need? Depends on what my resolution is that I'm shooting for and my accuracy needs are and that type of thing. Sometimes I just need enough measurements to make sure there are no mistakes in it. Other times I may need to measure something 16 direct and reverse, and that all the stuff be within 4 seconds of the mean, as the specifications were for the triangulation angle measurement. Okay? Now, a discrepancy is a difference between any two measurements in a set. So whenever I repeat stuff and I have redundancies in there, I can look at the difference between any two measurements, and that'll be a discrepancy. And usually that number, those numbers in itself don't tell me a lot. The discrepancy most people look at is, well, what's my highest one? What's my lowest one? And so that gives me my range of my measurements, which is kind of a really rough indicator of precision, but it's not really precision, but it's kind of gives you an idea. I fall within this range. The most probable value is the most likely value of the unknown measurement based on the measurement set. Now that I've measured something a bunch of times, what's the most likely value that that thing is? So if you Jim, if a client hires you to survey the exterior of their parcel so you can get bearings and distances around there for a meets and bounds description for conveyance purposes, and you measure each side a bunch of times, and you don't present them with a map that's got each side with 5 different distances on it. You're giving them a representation of that side with the best estimate of what that distance is based on all those measurements that you made. So we call it the most probable value. And in most cases, in an unweighted situation, we'll talk about weights in a little bit here, that's simply the arithmetic average. Okay, we add up all our measurements, M, we divide them by the number of measurements, N, and we get an average. And that's what our most probable value is for that set. Now, a residual is the difference between the most probable value and any measurement. So it's sort of like a discrepancy, except that one of those values that your measurements checked against is always the average, the most probable value. Now, because your most probable value is the average of all of them, some of your residuals are going to be positive, some of them are going to be negative. And if I make enough measurements, then if I add up all my residuals, what should they add up to? 0, right? Because that's somewhere, my average is somewhere in the middle of that type of thing. So just adding up the residuals by themselves don't tell us anything. However, the concept of least squares is that the most probable value is the number which minimizes the sum of the squared residuals. That is, if I were to square each of the residuals and add them all together and come up with a sum, that residual is going to be the smallest one of any other number I might use in place of the most probable value. I could use a different number, and when I compute the residuals with respect to those residuals are going to be the largest. So basically, the most probable value is the one that gives you the least sum of the squares. That's where the term least squares comes from, least sum of the squares of the residuals. Okay, and that comes from over the rainbow in statistics land. And it actually deals with the normal distribution curve and derivatives and all that kind of neat stuff that's way beyond the scope of anything we want to get into here. But basically, the simple application of it is the average is, the unweighted average is the one that minimizes the square of the residuals for any given measurement. We'll build on that and we'll extend that when we talk about networks where we're bringing together a bunch of measurements in the least square section next week. All right. Now, the standard deviation is an indicator of the precision or the spread of the measurement set. If I were to make an infinite number of measurements and were to compute my most probable value, and then from that compute all my residuals and then plot the residuals based on their frequency, I would get this bell-shaped curve. Okay, with this normal, it's called the normal distribution curve. In the middle here is my most probable value, and that's where most of my numbers are going to tend to be close to. There'll be some outliers that start to go farther away from here. How far and how fast depends on the spread of the numbers and that type of thing. But this curve has got an inflection point here. And what that inflection point means is it's where it turns from a concave curve pointed downward to a convex curve. So right there's where the slope changes of that curve. And that's symmetric on both sides because it's a normal shaped distribution curve. And that occurs at positive and negative standard deviation. And that's this equation right here. Now, the significance of that number is that it encloses 68% of the area under this entire curve. Now, the curve is asymptotic, okay, which sounds like a dirty word, but it's not. Just like rectilinear sounds like a bad word, but it's not. Asymptotic means it gets closer and closer, but never touches. Okay, this curve is closer and closer to zero, but it never touches. It goes out to infinity, it never touches. Okay, just like my daughter on her first date, always closer, never touching. And that happens on both sides here. So if we take the total area underneath this curve, 68% of it is bunched up right in here. That's a confidence interval. We're 68% certain that if we use the same equipment under the same condition, using the same procedures, that it will be 68% of the time within plus or minus a standard deviation of the most probable value. Now you'll see that there's standard deviation and there's standard error. And the difference between the two is whether we use n-1 down here or whether we use n down here. And that has to do with, are we talking about errors or are we talking about residuals? Residuals, if you think about it, is like an error because it's a difference between the most probable value, which is our estimate of the true value, and any measurement. So that's kind of like an error. And theoretically, what happens at this point is most adjustment textbooks and adjustment discussions kind of blur between the two and say, well, look, if you've done a really good job of getting rid of mistakes and systematic errors, then really the only thing that's left is random errors. So therefore, residuals are in fact errors, okay, based on our best guesstimate of what that true value is. And the more measurements you make, the truer that is. And what you'll see is that the standard error, instead of having n-1 down in here, we'll have an n in here. And in most statistics books, they'll tell you that the difference between standard error and a standard deviation is the standard error is used on a sample population, when you're only sampling a few things out of the larger population. That's where you do things like quality control in the factory. We're not going to, destructively test every single object that you build, but you're going to select a subset from that and test those. Whereas the standard deviation is used when you're using the entire population sets to generate the statistic, which is the case in surveying. We're using all of our measurements. But as you get bigger, as n starts to increase to get like 20 or so, the two become essentially the same thing. So again, it's like the more measurements we make, the smaller those random errors become, the closer we get to the true value. So we kind of treat that as an error, even though, it really technically isn't, but we'll think of it in those terms. Now, that gets us back to the conference zone. This is one of the things that when we talked about with the RTK stuff the other day, and also came up when we were talking about the LiDAR stuff the other couple weeks back here, dealing with the field checking of the LiDAR, the accuracy of the LiDAR data. And we talked about the 95% or the 90% confidence intervals and that type of thing. Well, the more common one that people use is the 95% confidence interval, which people refer to as a 2 sigma error, because it's about equal to twice the standard deviation, or 1.96. And what that does, it encloses 95% of the area underneath the distribution curve. So we can say basically, if we take the standard deviation and multiply it by 2, we can say that we're 95% certain that the true value is, the actual value is within this of our most probable value. Okay, we're 95% certain of that. If you want to be 100% certain, it would have to be all the area underneath this curve. Well, because it's asymptotic, it goes out to infinity. So to be 100% certain, you can say that I'm 100% certain that the true value is within plus or minus infinity of the measurement that I came up with, which technically is true, but it's not really very assuring. So that's normally why you see this 95% confidence interval, the 2 sigma one that's used. That's for a single measurement set. This is a single dimensional measurement set, like a distance or an elevation. Once you get into bivariate distributions, which are related in more than one dimension, we'll talk about that when we get to air ellipses, things get a little hinky because of the way that curve is shaped. Right? But for linear type of measurements, one-dimensional measurements, elevations, distances, and angle, and that type of thing, this works pretty well for a normal distribution curve. Now, the standard error and the mean. So we use this sigma standard deviation as a precision indicator. The smaller the standard deviation, the closer the stuff is grouped together. That makes our shot group come closer and closer together. It gets more accurate as well as it gets more precise. All right, so that's our precision indicator. Our accuracy indicator is related to that. It's called the error of the mean. So the standard deviation is for the measurement set, but we want to know not just how good is the measurement set, but how good is our estimate of what the most probable value is based on that measurement set. And that is related to the standard deviation. Oh crap, I didn't put the equation in here. Is it in the handout? Hopefully it's in the handout. This is the handout. Yes, it is in the handout. The error of the most probable value is equal to the standard deviation divided by the square root of n, which is the number of measurements. So it's related to standard deviation, which again, we're saying kind of using as an indicator of the accuracy, and the number of measurements. The n's on the denominator. So the more measurements we have, the bigger the denominator gets, and the smaller the error, the most probable value. So you can kind of think of it this way. Here's our normal distribution curve. Here's our standard deviation that represents 66 or 68% of the area of the curve. That's our confidence interval for the measurement set. And then the uncertainty in our most probable value is this guy right in here. That's how certain we are about that. So the more measurements we make, the tighter that gets right there, the better that gets. All right. Okay, let's look at a quick and dirty calculation with some of this stuff here. Yeah, as far as I wanted to, that's okay. We'll burn through this real quick. This is just an example of doing a set with 4 measurements. Now, statistically speaking, 4 measurements isn't enough. It really isn't enough to allow our error to really compensate in that type of thing. But in order to make this, to show the mechanics of going through all this, I want to keep the measurement set relatively small. So we have 4 measurements. We have 4 degrees of freedom because what we're measuring is, say, the length of something. So the first thing we'll do, we're going to add up all that stuff. Now, remember I said in significant figures that the sum can only be as accurate as your least accurate number, right? Well, if we look at this, the least accurate number is always in this spot here. So that means our sum is good to this spot right here. Now, here's another magical thing about making additional measurements, taking additional measurements. Each of these has got 4 significant figures. This one, on the other hand, has 5 significant figures. We've increased the number of significant figures by simply increasing the number of measurements that we made. So that's another thing about adding, what we're doing is we're refining that last estimate there. So if we take that to compute the average, we take that and we divide it by 4, which is an exact number, right? There's no error in that. That means that the answer is going to have 5 significant figures in it. So our answer, our most probable value is 45.662. Ta-da! Now, from this point on, I'm going to carry additional digits because these are intermediate calculations. I'm going to wait till I get to the end before I round my answer. To compute my residuals, I merely take and subtract each of the measurements from that most probable value. And I come up with these guys right here. And again, the more measurements I have a spread of positive and negatives. If I add them all together, I'll get 0, which doesn't tell me much of anything. However, if I square each one of those, they become positive. Okay? And when I add those up, this right here is the sum of the squares of the residuals. If I use any other number besides this one here to compute the residuals, this number here will be larger. This is the smallest possible number that will come out of here if I use the most probable value. So my standard deviation now, if I plug that number into here, n minus 1 at the bottom, I come up with plus or minus 0.012. Okay, so take out the same number of decimal places I have here. So that tells me I'm 68% confident that following these same procedures and all this kind of stuff, that I'll be within 68% of the time, I'll be within this of this up here. That's my range for this guy right there. Now, if I want to figure out how good that number is there, then if I take that standard deviation and divide it by the square root of the number of measurements, that tells me what my expected error in this is right here. This is how good my measurement set is. That's my precision. And this is my accuracy indicator for that guy right there. And you can see it, the more measurements I would make, the bigger this number becomes at the bottom here, then the smaller this number becomes. After a certain point, you get that point of diminishing returns, or after that, it doesn't really increase your accuracy that much more. But those initial first couple of them, instead of 4 measurements, if I did 6 or 8 measurements, it would drop down my random error tremendously in that first couple repetitions there. All right, now that's for what we call unweighted. That assumes that the quality of all the measurements are the same. We can mix together different quality measurements to come up with the best representation based on that population of unequal measurements, as long as we figure out some way to weigh them accordingly. All right. And when we get to the least squares network adjustment, that's one of the basic premises of doing a least squares adjustment, is how we can take individual measurements and give them specific weights to have different effects on the adjustment. So what happens is to compute, and we call the weights W, to compute a weighted average, we multiply the weight times its measurement and then divide it by the sum of the weights. Now, the weights, we can define a number of different ways. One way is if we've got standard deviations, the weights can be 1 over the standard deviation squared. If we're dealing with distances and we have precisions for distances, we can use 1 over the precision as a weight for that. If we're doing leveling we can use a distance criteria for the weighting for levels. The longer sites have less weight than the shorter sites do because it's harder to read the rod longer. There's all sorts of different weighting criteria, mechanisms that we can use. But in this case here, let's just use a real simple one. Say that we've got 3 different crews that measured a distance repeatedly by whatever methodology they used, and they came up with their own distances and standard deviations for those distances. Now, there is a typo on a handout. I have at 351.35. There should be 352.35. But if I just use a straight average in here, then I'll get this distance right here. Now, when I look at my measurements here, I see that my weakest one is this guy right here. That's got the largest standard deviation. My most precise set is this one here. That's my strongest one. But because I'm treating them all equally, I'm allowing this one here to pull all the other measurements towards it because it's a weaker distance. So if I want to create weights, I'm going to create weights by taking 1 over the standard deviation squared. Okay? So if I do that for each one of these, I wind up with these numbers here. And one of the other things that we normally do when we're dealing with weights, just to kind of keep down the number of calculations and stuff, because we're going to wind up with great big numbers. You're going to multiply this times this. We'll take and we'll just divide all the weights by the lowest one. Okay. They're all relative weights. So if I take all of them and divide it by 6.92, that reduces them a little bit at least. And then I wind up with a little bit more reasonable numbers to work with. So now if I take this times this, I get my weighted measurement. I add those up and I add up my weights. Now my weighted average is the sum, this thing here divided by the sum of the weights. And I get 352.284. Now notice it's different than this one by a pretty good chunk, 1600ths of a foot. That's because the greater weight now is on this guy right here, which pulls the average closer to it and further from the weaker one. We're still using the weaker one in there. It's just not contributing as much to the average that we're computing for that measurement set. All right. Ding, ding. All right, another way that we can use the statistics of an observation is we can compare one set of measurements to another set of measurements, something that's totally different, as long as it's the same type of measurement. So let's say crew A and crew B went out and they measured angles. Crew A did 2 direct and reverse, and they got 128 degrees, 18 minutes, 15 seconds for their angle, and with a standard deviation of 12 seconds. And crew B measured their angle somewhere else, 4 direct and reverse, had 996 degrees, 2 minutes, 40 seconds, with a standard deviation of 14 seconds. Okay. And ask you 2 questions. Which crew is better precision? Which is the more precise crew? Hop in there. Is there anybody left here yet? I can't tell. I can't see you. I'm assuming there's still, yeah, there's people out there.
Yeah, you're good.
Yeah, okay.
Chime in.
So, okay, which crew?
There's a couple of them in the chat. Sorry,
okay.
They're all saying B.
Why is B got better precision? You can't just answer one or the other. You got to give me an answer. You got to justify it, right?
And I would say probably because of the 4 direct and reverse.
Nah.
Hmm.
Now, what's our indicator? What's our indicator of precision?
Closest.
Standard deviations are indicator of precision, right?
Yeah.
Smaller the standard deviation, the better the grouping of measurement. Now, granted, theoretically, you could take more measurements and reduce your random error, but if you have more experience on one crew than another crew, then they may be getting better measurements with fewer measurements. See what I'm getting at? So it's a combination of stuff. So that's why we look at the statistics, not just the number of measurements. So the crew with the better precision is crew A because their standard deviation is smaller. Now, if I were to say which crew was more accurate, do we expect them to be more accurate? That's a different question, okay? Which is better expected accuracy? Now, in that case, what we want to look at is the error of the most probable value, right? Which is a function of the standard deviation and the number of measurements that they made. So in this case here, if we look at crew A, they have a good standard deviation, but they only have 4 measurements. So they've got 6 seconds of uncertainty or expected accuracy in that angle. Whereas crew B has got, because that 8 measurements, their standard deviation is a little bit worse, but they had more measurements. Theirs is only 5 seconds. So crew B has got a better accuracy, although crew A has got better precision. Let's remember those, the targets and stuff, precision and accuracy and stuff, they're not exactly the same thing. They're kind of related, but they are separate based on how the errors behave and that type of thing. So we can use that to compare different. Now, notice nowhere here did the size of the angle have anything to do with it. Okay, the angle size itself does not derive the accuracy of that angle measurement. Now, when we get into the angle measurement error propagation, we'll see how that does actually come into play, but it's based on the distances to the sites, to site points. All right, one other thing I'm going to go through real quick here, and I think I'll quit because it's taking a little bit longer than I thought. This is where most of the errors occur when people are doing calculations with, even basic calculations with statistics and stuff for random errors, is when they're dealing with angles. Because up until now, everything we've worked with, except for that last experiment, that last example right there, was we were dealing with a uniform unit system, like all distances, the lengths of things. When we're dealing with angles, we're dealing with mixed units, degrees, minutes, and seconds. They're separate ones put all together. It's sort of like expressing a distance in feet and inches. That's mixed units. So, and those mixed units represent different things when we get into angle measurement and that type of thing. Now, the most common way when I give students or in workshops, I have people do these calculations, and I have them compute for me an average of a couple of angles like this. And they immediately brute force it. Okay, they'll go through and they'll convert it to decimal. And for some reason, this magic number 3 is, and I think I mentioned this during my rules of construction thing, because there's always like the 3 conditions that have to be met for mine to be accepted, 3 conditions for common report and all that kind of stuff. 3 decimal places seems to be something that people settle on when they convert the degrees, minutes, and seconds to decimal degrees, and then work here and compute stuff this way. So this shows you all the numbers. And I think I have that in the handout, the complete numbers. I may or may not, but will be up on the, oh yeah, I do. Kind of in a condensed form there. This is doing it all longhand using 3 decimal places. And when you compute it back, you come with 35 degrees, 50 minutes, 43.42 seconds, which looks reasonable in the context of the stuff here, with a standard deviation of 14.4 seconds. Okay, so I'm going to keep that up here. Here's the same exact problem, same exact angles, but this time carrying 7 decimal places, which nobody wants to do because it's too much to write down or keep track of and that type of thing. So if I do it the same exact calculation, just carrying more decimal places, I come up with 35, 15, 42, and 11.7. So you can see that there's a difference of almost 3 seconds in here for the standard deviation, and better than a second here, which is within the accuracy of the numbers as they're expressed here. So the rule is carry 7 decimal places at least. Well, will 5 do it? Maybe. Will 6 do it? Probably. 8 will do it. Yeah, but there's a simpler way to do this. When we recognize that there are mixed units, The 35 doesn't change. The 15 doesn't change. What changes? It's just the seconds. So for just the seconds, let's just work with the seconds. So if we subtract 35, 15 off each one, then we're left with 30 seconds, 56 seconds, 35 seconds, 47 seconds. You add those up. You can do this one in your head, really, without even using a calculator. Divide that by 4, it gives you 42. You add that back to 35, 15, 42. It's the same thing we got carrying 7 decimal places, but we only had to carry just the seconds part. Plus, the other thing is, when we look at this, see that residual? What is that in? That's in decimal degrees. You look at that and say, what the hell does that mean? I had an angle in degrees, minutes, and seconds, but my residuals in decimal degrees, I can't see what that means. Over here, my residual is in seconds, and I can see what that means because it's in the same units that these guys are, right? So if I do my residuals, add those up, square them, divide it by 4 minus 1, take the square root, I get 11.7 seconds. I get the same thing I did with the 7 decimal places. So whenever you have mixed units, work with the smallest unit. The other ones don't change their exact values. Now I got a question for you. On this one right here, this one's slightly different because the degrees part stays the same, but the minutes differ. 3 minutes, 4 minutes, 4 minutes, 3 minutes. Then 58 seconds, 1 second, 3 seconds, 59 seconds. What should we subtract off as a constant off of this one? See, on this one back here, we subtracted off 35, 15 because I was constant here. What should we subtract off of this one right here? I'll get you started, 107 degrees. What next? What do we take off next? Or don't we? Dun, 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 dun.
107.03.
Take off 107.03, right? You take out 107.03, what does this one become? 58. What does this one become?
3.
61.
61. Yeah, right. I'm sorry.
63 and 59, right? We want to write in terms of the smallest unit, okay? So if we do that, then we go on to our division and we get 60.25, which means that it's 107.03 plus 62.5, which is 107.0402. So we still subtract off a constant, just in one case that we're going over the minutes, we count for that 60 in there. Okay. You could have subtracted 107.04 off of these, but then we'd have a negative here, positive, positive, and negative here, and you have to keep track of signs. Okay. But I just want to mention that because when you have mixed units like that, rather than brute force it through, work with the smallest unit, and you can not only not make the math mistake, but you can also see how the numbers make sense in the context of what you're working on. All right, I'm going to stop there and pick up on error propagation next time and burn through that real quick because that'll lead into least squares relatively well. Okay, are there any questions on any of this stuff here? Anybody do the homework yet? I'm not going to give the answers yet because some of the answers won't be until tomorrow, until next week. And maybe I'll throw up some more assignment type of stuff.
Yeah, that'll be nice. I know a while back Rob had his hand up, but I don't know if you still wanted to chime in on that or not, Rob. But
let's see. Do I have?
I put it up in answer to a question Jerry asked, like, who's an old fart that started measuring with a tape or something like that. But and then realized later I still have it up.
Oh, gotcha. Got it.
Actually, part of my surveying class I took was how to repair a broken tape. You know, we actually had the little handy anvil with the lead and all that kind of stuff, and we're gonna do all that crap.
That's awesome.
Yep, done that.
Oh yeah, the good old days.
Anybody have specific questions? If not, we can kind of hold them off until after next week. But
if this piques your interest, you have some questions about measurements or that type of stuff that may have come up with you, feel free to send them to me. I can incorporate them into the lecture, answer them individually and that type of stuff. Or if you have any questions on any of the assignments that I've put up, as long as if we've gotten to the material area, but you still don't understand how to do it, let me know. I will post the answers for all of them after next week's presentation.
Perfect.
Okay.
Schroeder had his hand up. Go for it, Schroeder.
Oh, yeah.
Yeah, so my tape repair was we had the lowest common denominator. The rear chainman repaired the tape and it had a ragged edge, so we cut it back to the next foot and put the splice in. And then things went to hell on the survey, and we finally took a look at the tape we were using, and we were short a foot.
As long as they do it on the foot mark, you can generally go back and correct those. It's when you're right in the middle of the tape and you got to look at now, did we have that one before or after? Was the measurement before or after where that patch is in there? Did we add that foot in there or not?
And that kind of induced systematic error can be from, I mean, using current technology, it could be using the wrong prism constant or having your prism flipped around where it's giving you a minus 30 instead of a 0 or a whatever.
Or the wrong adapter on your rod, so your antenna height's wrong by a constant. Yeah.
Yeah. Or rod bubble out of adjustment, or prism tribrach out of adjustment, which is systematic, but depending on which way you hold the rod, it becomes a random.
Yeah, there's another one that my students suffered from tremendously was parallax. If they didn't clear parallax in the scope, because that's a systematic error.
Right.
It's instrumental, but it behaves randomly when you're looking through the scope and that type of thing. So that would really throw them for a loop if they didn't clear that.
And then the manufacturers are trying to take care of it for us, like with these new little poles that you can be inclined. So it doesn't matter if your whole bubble's whacked out or if the person running the rod's not holding it straight.
That encourages you to be lazy, as far as I'm concerned. That encourages you to be lazy.
Well, I'm with you on that, but I'm old school, baby.
You know, I after 40 years of doing this, okay, I'll use the equipment to do that. But if this is somebody brand new starting out, man, they gotta suffer. They gotta realize that when they're out there chasing a thousandth of a foot on something that was laid in, that was only going to be good within a plus or minus a couple feet anyway. It's ridiculous to even do that, you know. So that leads up to the pin cushions and all that kind of stuff.
Yeah, well, this is where we're headed. That's for sure.
So when I was out in the field many years ago, wait, I'm muted. We all used 1/8-inch canyon lines, and standard with every truck was at least 2 little things of tape repair kits, because they broke all the doggone time. And yeah, you just had to pay attention to what you were doing, and good luck if you got a tape from somebody else's truck and you didn't know what they'd done to the doggone thing, because you had to find it out on your own.
The most frustrating thing is when you get a kink on it, I mean, you get a yank on it, it breaks real easy. But if you get that kink in there and you pull it, but you don't break it, you still get that little hump in there that no matter how hard you pull, you can't get that sucker out of there. So you've pretty much ruined the tape in that respect. You might as well break it and then patch it at that point.
Well, that and nobody wanted to use chain clamps. It was a loop around your hand.
Oh yeah, well the chain clamps are paying $1.
And if you did it right, you were okay. But if you didn't do it right, you have exactly what you said, Jerry, a big loop in the tape that you couldn't pull out no matter how hard you pulled.
And that's why there was calibration baselines.
I think we still have one here in Reno, but I don't know if anyone's used it within the last 20 years.
Yeah, we have one outside of, just down the street from where I taught at MATC, and we used to go out there every year and take a couple of our 12 stations out there just to calibrate them. Then we do our local baseline calibration too, just to show them the difference between them. But the roads got wider and wider, and pretty soon the points themselves got into the pavement and that type of thing, so they weren't real safe to use. But there's still some demand for them around here. I get people call up every now and then or send me an email asking me about information about where the local baselines are.
Nice.
I'm really lucky. I got one baseline outside of Lethbridge where I teach, and one baseline outside of Cranbrook, BC where I work. So
nice.
Kind of handy.
There you go.
Where do you teach, Andrew?
Lethbridge, Alberta.
Okay.
Lethbridge College.
Oh,
nice.
Cool.
You familiar with my? Are you familiar with my website at all, Andrew? But
I am now.
okay.
Yeah, I just threw it up in the chat as well, and then
because I started putting that together a number of years ago, and I've been getting a lot of good feedback on it. As a matter of fact, we're adapting it for use, or we're incorporating it into the Learn CST stuff for the CST program and that type of thing. So I'm in a process right now putting together some stuff on datums and formal coordinate systems that are going up on there too. So
nice.
Absolutely. Yeah, I love your website. I checked it out a little bit. I'm also processing some LiDAR data as we're doing this as well. So kind of a busy Monday.
There you go. Well, cool. I definitely appreciate it, Jerry.
Not a problem.
Yeah,
Enjoyed it.
we'll pick it up again next week and keep figuring out the random errors.
Okay. All right.
Awesome. All right, guys. Have a good night.
Jerry. Thanks, Trent.
Thank you, Jerry.
You're welcome. Let's see. I have to.